Industrial progress has never been driven by safety alone. Many of the machines that powered mining, steelmaking, manufacturing, and construction were adopted because they worked, long before anyone understood how deadly they could be. These machines delivered unprecedented output by placing human operators inches from molten metal, explosive pressure, crushing force, toxic chemicals, and unstoppable motion. In many cases, injury and death were not accidents, but expected risks built into the process itself. Crews learned to work around machines that could not be stopped quickly, controlled precisely, or made forgiving. Some were eventually redesigned or replaced. Others were abandoned entirely after their human cost became impossible to ignore. This list examines industrial machines whose efficiency came at such extreme danger that their use reshaped safety laws, labor practices, and the limits of what industry was willing to accept. Bessemer converter. Molten steel at the edge of human control. The Bessemer converter was one of the most revolutionary machines of the industrial age, but it was also among the most dangerous ever placed into routine operation. Introduced in the mid-19th century, it transformed steel production from a slow, labor-intensive craft into a high-speed industrial process. In doing so, it pushed molten metal handling to a scale and volatility that workers struggled to control. At its core, the Bessemer converter was a massive, pear-shaped vessel lined with refractory material and mounted on pivots. Molten pig iron was poured inside, after which powerful blasts of air were forced upward through the liquid metal. This air burned away carbon and impurities, rapidly converting iron into steel. The reaction was violent, spectacular, and extremely unpredictable. Temperatures exceeded 1,600 degrees Celsius, and the process produced towering flames, blinding light, and showers of sparks. The danger lay in the speed and intensity of the reaction. Unlike later steelmaking methods, early Bessemer operations offered almost no precise control over chemistry or temperature. A slight miscalculation in timing or composition could cause the entire vessel to erupt. Slag and molten steel were frequently expelled from the mouth of the converter, sometimes in explosive bursts that killed or severely burned nearby workers. Tilting the converter added another layer of risk. The machine had to be rotated manually, or with early mechanical systems to pour finished steel into molds. Mechanical failure, worn pivots, or operator error could cause the vessel to tip uncontrollably, spilling tons of molten metal across the shop floor. Such accidents often resulted in multiple fatalities and widespread destruction of equipment. Airborne hazards were constant. The process released toxic gases, including carbon monoxide, and filled the work area with fine particulate matter. Protective equipment was minimal or non-existent, leaving workers exposed to burns, lung damage, and long-term illness. Visibility during a blow was often so poor that operators relied on experience and sound rather than sight to judge when the reaction was complete. Because of these risks, many early steelworks recorded extraordinarily high injury and death rates. Entire crews could be lost in a single catastrophic failure. Some factories earned reputations as places where survival depended as much on luck as skill. In several regions, experienced workers refused assignments near converters, considering them machines that could turn lethal without warning. Over time, improved linings, instrumentation, and safety practices reduced the danger, and newer processes eventually replaced the Bessemer method. Yet, its legacy remains stark. The Bessemer converter demonstrated that industrial progress often advanced faster than safety, placing human lives at the edge of control in the pursuit of mass production. Steam hammer. Unforgiving power in early heavy industry. The steam hammer was one of the most awe-inspiring and feared machines of early heavy industry, embodying raw mechanical power with almost no tolerance for human error. Introduced in the mid-19th century, it allowed manufacturers to forge massive metal components that had previously been impossible to shape. At the same time, it created working conditions where a single mistake could result in instant death. At its simplest, a steam hammer consisted of a heavy ram driven vertically by steam pressure, raised and dropped onto heated metal placed on an anvil. Some hammers weighed several tons and delivered blows powerful enough to shape ship shafts, locomotive components, and artillery parts. Early versions had limited control over stroke speed and impact force, relying heavily on the skill and reflexes of the operator. The danger came from the combination of extreme mass and imperfect control. Early steam valves were crude, and pressure regulation was inconsistent. A misjudged valve input or mechanical fault could cause the hammer to descend unexpectedly or with far greater force than intended. Workers positioning hot metal beneath the ram often had only seconds to react, and many were crushed before they could escape. Flying debris was another constant threat. When struck improperly, red-hot metal could fracture or eject fragments at high speed, acting like shrapnel. These fragments caused severe burns, broken bones, and fatal injuries well beyond the immediate work zone. Protective barriers were rare, and eye or body protection was minimal. Mechanical failure compounded the risk. Worn guides, cracked frames, or steamline ruptures could cause catastrophic collapse. In some recorded incidents, entire hammer assemblies broke loose, destroying surrounding structures and killing multiple workers. Steam itself posed hazards, as pipe failures released scalding vapor capable of inflicting lethal burns in seconds. Noise and vibration added long-term dangers. Steam hammers produced deafening impacts that damaged hearing permanently. Continuous ground vibration weakened nearby buildings and fatigued machine components, increasing the likelihood of sudden failure. Workers often developed chronic injuries to joints and nerves from years spent in close proximity to the machine. Because of these risks, steam hammer operation demanded highly experienced crews, yet even skilled teams were not immune to accidents. Many industrial records describe fatalities as an accepted cost of production. Some factories rotated workers frequently, knowing prolonged exposure increased the chance of serious injury or death. Later, innovations introduced hydraulic presses and improved control systems that reduced unpredictability. Compared to those machines, the steam hammer came to be seen as brutally inefficient and unnecessarily dangerous. The steam hammer represents a period when industrial power outpaced safety engineering. It delivered unmatched force but demanded absolute precision in an era that could not reliably provide it. In early heavy industry, the steam hammer was not merely a tool, but a constant reminder that progress often came at a lethal human cost. Hydraulic forging press, crushing force with no margin for error. The hydraulic forging press marked a major technological leap in heavy industry, replacing the violent impact of steam hammers with controlled, sustained pressure. While it offered greater precision and the ability to forge enormous components, it also introduced a different and equally lethal danger: slow, unstoppable force with absolutely no margin for human error. Developed in the late 19th and early 20th centuries, hydraulic forging presses used high-pressure fluid systems to apply crushing force to heated metal. Instead of striking blows, the press compressed material steadily, allowing manufacturers to shape massive shafts, armor plates, and structural components used in ships, power plants, and heavy machinery. Some presses exerted forces measured in thousands of tons, dwarfing anything a human could resist or escape once motion began. The primary danger lay in the nature of hydraulic power itself. Unlike impact machines, a hydraulic press does not recoil or hesitate. Once engaged, it continues its stroke with relentless force until the cycle is completed or the system fails. If a worker's hand, arm, or body part was caught in the press, there was no chance of survival. Injuries were instantaneous, catastrophic, and irreversible. Early hydraulic presses lacked modern interlocks, sensors, and emergency stop systems. Control valves were often manual, slow to respond, or positioned far from the working area. A delayed reaction of even a fraction of a second could result in fatal crushing. Many presses required workers to manually position red-hot metal between dies, placing them dangerously close to the compression zone. Hydraulic system failures introduced additional hazards. Ruptured hoses or seals could release high-pressure fluid violently, injecting oil into the skin or spraying flammable mist near furnaces. Sudden pressure loss could also cause uncontrolled movement of massive components, leading to secondary crushing incidents or structural collapse. The scale of these machines amplified every risk. Large presses were often housed in deep pits or reinforced halls, with moving platens weighing tens of tons. Falling components, misaligned workpieces, or die failures could kill workers several meters away. Because the press operated silently compared to steam hammers, danger often came without audible warning. Industrial accident records from early forging facilities document numerous fatalities associated with hydraulic presses, often involving experienced workers. The machine's predictability created a false sense of safety, leading operators to underestimate how quickly conditions could turn deadly. Over time, improved guarding, two-hand controls, pressure monitoring, and automated material handling reduced the risk. Even so, hydraulic forging presses remain among the most dangerous machines in heavy industry, requiring strict procedures and constant vigilance. The hydraulic forging press demonstrated that control does not equal safety. By replacing explosive force with crushing inevitability, it introduced a machine that demanded perfection every time. In environments where humans were still integral to the process, that demand proved unforgiving, cementing its reputation as an industrial tool with no tolerance for mistakes. Open hearth furnace, prolonged exposure to extreme heat and toxic gases. The open hearth furnace was once the backbone of global steel production, enabling mass manufacture on an unprecedented scale. At the same time, it earned a grim reputation as one of the most dangerous machines in industrial history. Unlike sudden, catastrophic hazards, the open hearth furnace subjected workers to slow, cumulative exposure to extreme heat, toxic gases, and exhausting labor that steadily destroyed health and lives. Introduced in the late 19th century, the open hearth process used large, shallow furnaces to melt pig iron and scrap steel using regenerative heating. Flames and exhaust gases were routed through brick-lined chambers, allowing heat to be recycled and temperatures to exceed 1,600 degrees Celsius. Furnaces often operated continuously for weeks, producing enormous volumes of molten steel. The danger began with heat exposure. Workers labored only meters from open furnace doors, where radiant heat could reach levels capable of causing burns in seconds. Temperatures on the shop floor regularly exceeded human tolerance, forcing crews to rotate constantly to avoid collapse. Heat exhaustion, dehydration, and heat stroke were common, and fatal incidents were often recorded simply as industrial illness. Toxic gases made conditions even worse. The process released large quantities of carbon monoxide, sulfur dioxide, nitrogen oxides, and fine metallic dust. Ventilation was primitive by modern standards, allowing invisible gases to accumulate inside furnace halls. Carbon monoxide poisoning was a constant threat, often causing dizziness, confusion, and loss of consciousness without warning. Workers frequently collapsed into dangerous zones, where they were exposed to molten metal or heavy machinery. Manual labor near the furnace added physical risk. Charging the furnace involved dumping raw materials from above, creating falling hazards and sudden flare-ups when moisture contacted molten steel. Slag removal required workers to approach open ports and manipulate molten waste, risking splashes that could burn through clothing and flesh instantly. Visibility was often poor. Intense glare, smoke, and heat distortion made it difficult to judge distances or detect hazards. Communication relied on hand signals and shouted warnings that were easily missed in the noise and chaos of the shop. Many accidents occurred simply because workers could not see or hear danger in time. Long-term health effects were severe. Prolonged exposure to heat and fumes caused chronic respiratory disease, cardiovascular damage, and neurological problems. Many workers aged prematurely, with life expectancy significantly lower than the general population. By the mid-20th century, safer and more efficient processes such as basic oxygen steelmaking replaced the open hearth furnace. Its decline was driven not only by productivity, but by recognition that the human cost was unacceptable. The open hearth furnace stands as a reminder that industrial danger is not always explosive or dramatic. Sometimes it is relentless, invisible, and endured over years. slowly consuming the people who kept the furnaces burning. Bucket wheel excavator, a moving city that could not be stopped. The bucket wheel excavator is one of the largest land machines ever built, a colossal industrial system designed to remove entire landscapes piece by piece. While remarkably efficient at large-scale excavation, it earned a reputation as one of the most dangerous machines in heavy industry because of its sheer mass, continuous motion, and the near impossibility of stopping it once in operation. Developed in the early to mid-20th century for open-pit mining and large earth-moving projects, bucket wheel excavators were engineered to extract massive volumes of material continuously. A rotating wheel, fitted with dozens of steel buckets, cut into earth, coal, or overburden, lifting material onto conveyor systems that stretched hundreds of meters. Fully assembled, some machines exceeded 200 meters in length and weighed more than 10,000 tons, effectively functioning as mobile industrial cities. The primary danger lay in scale and inertia. Unlike smaller machines, a bucket wheel excavator cannot stop quickly. Once the wheel, conveyors, and superstructure are in motion, shutting down the system takes time. If a worker entered a restricted zone or fell onto a moving conveyor, there was little chance of rescue before catastrophic injury occurred. Crushing, entanglement, and falls were the most common fatal accidents. Visibility was another major hazard. Operators controlled the machine from elevated cabins with limited lines of sight. Blind spots existed across vast sections of the structure, especially near the wheel and conveyor transfer points. Ground crews working below were often invisible to operators, relying on strict procedures and radio communication that, if broken, could lead to fatal consequences. Mechanical failure amplified the risk. Conveyor belts under extreme tension could snap without warning, whipping steel cables and rubber belts across work areas. Structural fatigue, especially in early designs, occasionally caused partial collapses that destroyed nearby equipment and killed workers. Because repairs often had to be conducted while other systems remained operational, maintenance itself was a high-risk activity. Environmental instability added another layer of danger. Bucket wheel excavators operate on shifting ground, often on unstable overburden or mined terrain. Ground collapse beneath the machine could tilt or derail the entire structure. In several documented incidents, excavators tipped over or sank into the ground, trapping crews and causing extensive fatalities. The psychological danger was constant. Workers were surrounded by slow-moving but unstoppable machinery, where danger was not sudden but inevitable once mistakes occurred. Fatigue from long shifts increased the risk of missteps near conveyors, ladders, and rotating systems. Modern safety systems, sensors, and automated shutdowns have reduced risks, but the fundamental danger remains. The machine's size ensures that human error is unforgiving. The bucket wheel excavator represents industrial power taken to its absolute limit. It was efficient beyond comparison, yet so vast and relentless that once it moved, it dominated everything around it. In that sense, it was not just a machine, but a force of nature, one that could not be reasoned with or stopped in time when things went wrong. Early coal-cutting machine. Mechanized death in confined tunnels. The early coal-cutting machine was introduced as a solution to the brutal physical demands of manual mining, but it quickly became one of the most feared machines underground. Designed to mechanize coal extraction in narrow tunnels, it brought industrial power into spaces never meant to contain moving machinery, turning already dangerous mines into environments where death could arrive suddenly and without escape. Coal-cutting machines emerged in the late 19th and early 20th centuries, using rotating chains, discs, or cutter bars fitted with steel teeth to slice coal from seams. Powered by compressed air or electricity, these machines advanced through tunnels only a few meters wide and barely tall enough for a standing worker. Unlike surface machinery, miners could not step aside easily. Walls, ceilings, and equipment left no room to retreat when something went wrong. The most immediate danger was physical contact. Exposed cutting chains and rotating drums operated inches from workers responsible for guiding, stabilizing, and clearing debris. Guards were minimal or non-existent, and a slip, stumble, or moment of inattention often resulted in crushed limbs, amputations, or fatal injuries. In the confined space, co-workers could not always reach the victim in time to shut down the machine. Electrical hazards were severe. Early insulation was poor, and cables ran across wet, uneven ground. Sparks from motors or damaged wiring could ignite methane gas, a constant presence in coal mines. Explosions, triggered by coal cutters, killed entire crews, collapsing tunnels and trapping survivors far from rescue. Noise and vibration added long-term danger. Machines produced intense sound levels that damaged hearing permanently, while constant vibration weakened tunnel supports. Collapses caused by machine-induced instability were common, burying workers beneath tons of rock and coal with little chance of survival. Visibility was another critical problem. Coal dust filled the air during cutting operations, reducing vision to a few feet. Headlamps provided limited illumination, and warning signals were often missed in the noise. Workers sometimes stepped directly into the path of moving machinery without realizing it until too late. Maintenance was particularly deadly. Repairs often had to be performed underground with power systems partially active. A sudden restart, pressure surge, or falling debris could kill mechanics instantly. Many accident reports describe experienced workers crushed during routine servicing. The psychological toll was constant. Miners worked knowing that machinery left no margin for error and that escape routes were narrow, dark, and unstable. Fatigue from long shifts increased the likelihood of mistakes, and injury rates soared wherever machines were introduced too quickly without safety redesign. Eventually, improved guarding, remote controls, and better ventilation reduced the danger. However, early coal-cutting machines earned their reputation honestly. They mechanized productivity, but in doing so, they turned confined tunnels into lethal industrial traps, where progress advanced faster than the ability to protect human life. Mechanical power press, instantaneous crushing and sheet metal work. The mechanical power press became one of the most productive machines in modern manufacturing, but it also earned a grim reputation as one of the most dangerous ever used on factory floors. Designed to stamp, punch, or form sheet metal at high speed, the press delivered immense force in fractions of a second, leaving no opportunity for human reaction once a cycle began. Mechanical power presses emerged in the late 19th and early 20th centuries as mass production expanded. Driven by flywheels, crankshafts, and mechanical linkages, these machines converted rotational energy into rapid, vertical motion. With a single stroke, a press could cut or shape metal with tons of force, repeating the action hundreds of times per hour. Productivity increased dramatically, but safety lagged far behind. The primary danger of the mechanical press was its speed. Unlike hydraulic presses, which move relatively slowly, mechanical presses complete their downward stroke almost instantly. If a worker's hand or fingers were inside the die area when the press engaged, injury was unavoidable. Crushing, amputations, and fatalities occurred so quickly that witnesses often described accidents as silent, instantaneous events. Early presses were commonly foot-operated. A single misstep, slip, or loss of balance could activate the machine unintentionally. In crowded factories, vibration from nearby equipment sometimes triggered engagement. Many workers lost fingers or hands simply by adjusting material too close to the die while the press was still energized. Mechanical failure increased the risk. Worn clutches, broken springs, or damaged linkages could cause a press to double cycle, repeating a stroke without warning. In such cases, even experienced operators following normal procedures were injured or killed. Because presses were expected to run continuously, maintenance was often delayed, compounding the danger. Guards and safety devices were rare in early installations. Employers relied on operator skill and speed rather than physical protection. Production quotas encouraged workers to bypass rudimentary safety features, placing hands closer to dies to increase output. In many factories, injury was considered an accepted cost of efficiency. The press also posed long-term risks. Repetitive motion caused chronic injuries, while constant noise damaged hearing. Stress levels were high as workers operated knowing that a moment's distraction could permanently end their ability to work. Accident records from the early to mid-20th century show mechanical power presses among the leading causes of industrial amputations. Entire categories of workplace safety laws were later written specifically in response to press-related injuries. Modern presses now incorporate light curtains, two-hand controls, interlocks, and automated feeding systems. These innovations dramatically reduced accidents, but they came only after decades of human cost. The mechanical power press illustrates the most unforgiving form of industrial danger, force applied faster than human reflex. In sheet metal work, it transformed productivity but demanded absolute precision from operators in environments that rarely allowed it, cementing its reputation as a machine that punished even the smallest mistake instantly. Cable logging yarder, high tension, steel lines that snapped without warning. The cable logging yarder was one of the most dangerous machines ever used in the timber industry, transforming forests into industrial work zones dominated by extreme tension, unpredictable forces, and sudden, lethal failure. Designed to haul massive logs across steep and inaccessible terrain, yarders relied on steel cables stretched under enormous load, creating conditions where death could arrive without sound or warning. Cable yarders became widespread in the early to mid-20th century as logging expanded into mountainous regions where wheeled vehicles could not operate. A yarder consisted of a tall steel tower mounted on a tracked or wheeled base powered by large winches that reeled in cables stretching hundreds of meters through dense forest. Logs were attached to these cables and dragged, lifted, or suspended as they were moved toward collection points. The primary danger came from cable tension. Steel lines were placed under immense load, often near their material limits. If a cable failed due to wear, improper splicing, corrosion, or overload, it snapped violently, whipping through the air with explosive force. These recoiling lines could cut through trees, equipment, and human bodies instantly. Workers caught in the snapback zone rarely survived. Visibility made the risk worse. Logging sites were noisy, chaotic environments filled with moving logs, falling debris, and limited sightlines. Ground crews often worked far from the yarder operator, relying on shouted commands or hand signals. A worker could unknowingly step into a danger zone moments before a cable failed or a log surged unexpectedly. Logs themselves became weapons. When dragged uphill or suspended improperly, they could break loose, roll downhill, or swing uncontrollably. A single shifting log could knock workers off slopes or pin them against trees. Combined with snapping cables, these forces made logging sites among the deadliest industrial workplaces of their time. Mechanical failure compounded the threat. Winch brakes could slip, drums could jam, and anchors could pull free from unstable ground. Any failure instantly transferred massive energy into the system, often toward the nearest workers. Maintenance was especially hazardous, as crews had to work near tensioned lines that could engage unexpectedly. Environmental conditions added further danger. Rain, snow, and mud reduced footing on steep slopes, while cold temperatures made steel cables brittle and more prone to failure. Fatigue from long shifts increased mistakes, and emergency response in remote forest locations was slow or non-existent. Because of these risks, logging fatalities were accepted as inevitable in many entire crews were lost in single incidents, and experienced workers carried scars and amputations as evidence of survival rather than safety. Modern yarders use improved materials, remote controls, and stricter safety, but the fundamental danger remains. The cable logging yarder represents an industry where invisible forces held in steel determined life or death. It stands as a machine that demanded constant vigilance, yet punished even perfect behavior when materials failed without warning. Rotary cement kiln. Continuous operation in lethal thermal conditions. The rotary cement kiln is one of the most unforgiving machines ever used in industrial operating continuously at temperatures and conditions that leave virtually no margin for human error. Essential to modern construction, it enabled mass cement production on a global scale, but it also exposed workers to extreme heat, toxic atmospheres, and mechanical hazards that made it one of the most dangerous industrial systems to maintain or operate. Rotary kilns were introduced in the late late 19th and early 20th centuries, placing earlier batch-style cement furnaces. Consists of a massive steel cylinder, often exceeding 60 meters in length, slowly rotating on heavy rollers while inclined slightly downward. Raw materials are fed into the upper end and move gradually toward the lower end as the kiln turns. Inside, temperatures reach approximately 1,450 degrees Celsius, hot enough to partially melt rock, and the primary danger came from continuous operation. Unlike furnaces that could be shut down regularly, rotary kilns were designed to run non-stop for months at a time. Shutting one down risked structural damage, so maintenance and inspections were often performed while the kiln remained hot and rotating. Workers were forced to operate near surfaces radiating lethal heat, where a single misstep could cause severe burns or death within seconds. Mechanical hazards were constant. The kiln's slow rotation masked enormous momentum. If a worker became caught in rotating components, escape was impossible. Support rollers, drive gears, and exposed couplings crushed or pulled in anyone who slipped or misjudged distance. Early installations lacked guarding, and many accidents involved workers being dragged beneath the rotating shell. Toxic exposure added another layer of danger. Kilns emitted large quantities of dust, carbon monoxide, sulfur compounds, and nitrogen oxides. Ventilation systems were primitive, allowing gases to accumulate in confined spaces around the kiln. Carbon monoxide poisoning was a frequent cause of collapse, often leading workers to fall into active machinery or hot zones before rescue was possible. Refractory failure created sudden, catastrophic hazards. The kiln's interior lining could crack or detach without warning, releasing molten material or exposing steel shell sections to extreme heat. In several documented incidents, shell deformation or rupture caused massive fires and fatal injuries to nearby crews. Environmental conditions worsened risk. Cement plants were noisy, dimly lit, and coated in fine dust that reduced visibility and footing. Fatigue from long shifts increased the likelihood of mistakes, while emergency response was difficult due to the kiln's size and heat. Modern kilns incorporate better insulation, automation, and monitoring systems, but the core danger remains unchanged. The rotary cement kiln demanded human presence in an environment fundamentally hostile to life. It stands as a machine that achieved industrial efficiency through relentless heat and motion, exacting a heavy human cost in exchange for continuous production. Steam locomotive boiler, explosive pressure on the open railway. The steam locomotive boiler was one of the most dangerous machines ever operated in public space, carrying explosive force through cities, countryside, and crowded rail yards. Machinery confined to industrial buildings, the boiler traveled openly at speed, containing lethal pressure only meters away from crews, passengers, and bystanders. When it failed, the results were often catastrophic. Steam locomotive boilers emerged in the early 19th century as rail transport expanded rapidly. A boiler consisted of a large steel vessel filled with water, heated by a firebox burning coal or wood. As water turned to steam, pressure built to drive pistons and wheels. Early boilers routinely operated at pressures exceeding what contemporary metallurgy could reliably contain. Riveted joints, variable steel quality, and inconsistent manufacturing made failure a constant risk. The primary danger was explosion. If pressure exceeded structural limits or water levels dropped too low, the boiler could rupture violently. Such explosions were not simple leaks. They were instantaneous releases of stored energy equivalent to high explosives. Entire boiler shells were launched hundreds of meters, locomotives were torn apart, and crews were often killed instantly. Passengers in nearby cars and people standing near tracks were frequently caught in the blast. Boiler failures were difficult to predict. Corrosion weakened internal surfaces over time, while scale buildup reduced heat transfer and hotspots that could fail without warning. Water level gauges were unreliable, and human judgment played a critical role. A distracted or fatigued engineer could allow water to drop below safe levels, exposing boiler plates directly to fire, triggering explosion within minutes. Operating conditions intensified the risk. Locomotives faced constant vibration, thermal cycling, and mechanical stress while traveling long distances. Emergency braking, steep gradients, or sudden throttle changes placed additional strain on boilers already operating near their limits. Repairs were often rushed to keep trains running, and inspection standards varied widely. The open nature of railways amplified the danger. Boilers exploded near stations, crossings, or maintenance yards, turning routine operations into mass casualty events. Some explosions destroyed buildings adjacent to tracks and killed people with no connection to railway work. These incidents shocked the public and earned steam locomotives a reputation as moving bombs. Crew survival depended largely on luck. Engineers and firemen worked directly beside the boiler, feeding fuel and monitoring gauges under intense heat. Many carried lifelong injuries from steam burns, scalding water releases, or partial ruptures that did not fully explode. By the early 20th century, stricter inspection laws, improved metallurgy, and better safety valves reduced explosions, but they never eliminated the risk entirely. Only the eventual replacement of steam by diesel and electric traction removed the hazard. The steam locomotive boiler stands as a reminder that industrial power once moved freely through public spaces with minimal protection. It delivered progress at speed, but carried explosive danger wherever the rails led. Industrial guillotine shear, precision cutting with fatal consequences. The industrial guillotine shear was designed to deliver clean, precise cuts through thick metal with absolute efficiency. In practice, it became one of the most feared machines on factory floors, capable of inflicting fatal injuries in an instant. Its danger did not come from malfunction or excess force, but from how perfectly it performed its intended task, leaving no possibility of human reaction once activated. Guillotine shears became common in the late 19th and early 20th centuries as sheet metal production expanded. The machine operated on a simple principle. A massive steel blade descended vertically against a fixed lower edge, slicing through metal using enormous force. Early shears were powered mechanically or hydraulically and were often foot-operated, allowing rapid, repetitive cutting in high-volume workshops. The primary hazard was the blade itself. Once a cutting cycle began, the descending knife moved too fast for any human to withdraw a hand or arm. If an operator's fingers were positioned incorrectly while aligning material, injury was unavoidable. Amputations were common, and fatalities occurred when workers leaned too far into the cutting zone or slipped on oil-covered floors during operation. Lack of guarding greatly increased risk. Early guillotine shears were typically open at the front, leaving the blade fully exposed. Safety interlocks, light curtains, and two-hand controls did not yet exist. Productivity demands often encouraged operators to hold material close to the blade for accuracy and speed, placing their hands directly beneath the cutting path. Mechanical faults added further danger. Worn clutches, sticking valves, or damaged linkages could cause unexpected blade drops. In some cases, blades fell under their own weight when locking mechanisms failed, crushing hands or heads without warning. Because the blade assembly was extremely heavy, even partial movement could cause fatal injuries. Maintenance posed its own lethal risks. Changing blades or clearing jams required workers to place themselves directly under the cutting mechanism. Lockout procedures were poorly understood or ignored, and accidental activation during servicing killed experienced mechanics who believed the machine was safe. Environmental conditions worsened the threat. Metalworking shops were noisy, crowded, and filled with sharp offcuts. Communication relied on shouted warnings, easily lost in machinery noise. Fatigue from long shifts increased mistakes, and repetitive work dulled attention, making split-second errors more likely. Accident records from the early to mid-20th century list guillotine shears as a leading cause of industrial amputations. Entire safety regulations were later written specifically in response to injuries caused by these machines. Modern shears now incorporate guarding systems, automated feeding, and redundant safety controls. The industrial guillotine shear demonstrated that precision itself can be deadly. By combining perfect alignment, immense force, and rapid motion, it punished even minor lapses with irreversible consequences. In the pursuit of efficiency, it became a machine where accuracy and danger were inseparably linked. Blast furnace charging system. Falling loads above molten iron. The blast furnace charging system was one of the most perilous mechanisms in early iron and steelmaking, operating at the intersection of gravity, extreme heat, and heavy industrial motion. Its purpose was simple in theory: deliver iron ore, coke, and limestone into the top of a blast furnace continuously. In practice, it placed workers directly above molten iron, under conditions where a single mistake or failure was almost always fatal. Early blast furnaces required constant charging to maintain stable chemical reactions. Raw materials were lifted using skips, hoists, or inclined rail systems and dumped into the furnace throat through bell mechanisms or open hoppers. These systems operated tens of meters above directly over molten iron, exceeding 1,500 degrees Celsius. Unlike later enclosed designs, early charging platforms were exposed, crowded, and manually operated. The most immediate danger came from falling loads. Charging skips often carried several tons of material. Worn cables, failed brakes, misaligned rails, or operator error could cause a skip to drop without warning. When this occurred, the load fell with unstoppable force, crushing workers, collapsing platforms, or knocking crews into furnace openings. Survival was virtually impossible. Explosive hazards were equally severe. Moisture trapped in ore or coke could flash into steam upon contact with the furnace interior, violently ejecting hot gases, slag, and burning material upward. These eruptions, known as furnace bursts, could engulf charging platforms in fire and debris. Workers caught in such events suffered severe burns or were thrown from elevated positions. Visibility and communication failures increased risk. Charging areas were filled with smoke, dust, glare, and heat distortion. Workers relied on shouted commands or hand signals that were easily lost in noise. A mistimed signal could release material while people were still in exposed positions, turning routine operations into fatal accidents. Structural failure added another layer of danger. Charging floors, rails, and support beams were exposed constantly to vibration, corrosive gases, and radiant heat. Metal fatigue was common. Entire platforms occasionally collapsed without warning, sending workers falling directly toward the furnace throat or onto moving charging equipment. Maintenance was particularly deadly. Because shutting down a blast furnace was costly and time-consuming, repairs were often conducted while the furnace remained active. Mechanics worked above molten iron, surrounded by suspended loads and moving machinery. Many fatal incidents occurred during routine inspections or cable replacements. Long-term exposure compounded immediate risks. Carbon monoxide and other furnace gases caused dizziness or unconsciousness, leading workers to fall from heights or into machinery. Heat stress and exhaustion further reduced reaction time. Modern blast furnace charging systems are enclosed, automated, and remotely controlled. Early systems were not. They achieved industrial efficiency by placing human labor at the most dangerous point of the process. The blast furnace charging system stands as a stark example of early industrial design where productivity outweighed survivability. It functioned by suspending massive loads above molten iron and human life simultaneously, earning its reputation as one of the most lethal machines ever used in heavy industry. Early chemical reactor vessels, unstable reactions without safeguards. Early chemical reactor vessels were among the most dangerous machines ever introduced into industrial production, operating at the intersection of heat, pressure, and poorly understood chemistry. To accelerate reactions at scale, these vessels often pushed materials beyond known limits without reliable controls, turning routine manufacturing into a constant risk of explosion, poisoning, or catastrophic release. During the late 19th and early 20th centuries, chemical industries expanded rapidly to meet demand for fuels, fertilizers, explosives, dyes, and synthetic materials. Reactor vessels were designed as sealed containers where reactions could occur under elevated temperature and pressure to increase efficiency. However, chemical engineering as a discipline was still in its infancy. Reaction kinetics, thermal runaway behavior, and pressure dynamics were often poorly understood or guessed through trial and error. The primary danger was uncontrolled reaction escalation. Many early reactors lacked temperature sensors, pressure relief valves, or automated shutdown systems. If a reaction began generating heat faster than it could be removed, pressure rose rapidly inside the vessel. Steel shells, riveted seams, or cast iron fittings could fail suddenly, releasing explosive force comparable to industrial bombs. Entire buildings were destroyed in single reactor failures, killing workers instantly. Toxic exposure added another layer of lethality. Early reactors processed substances such as chlorine, ammonia, sulfur compounds, and volatile hydrocarbons. Leaks from corroded joints or cracked vessels released invisible clouds that burned lungs, blinded eyes, or suffocated workers within minutes. Protective equipment was minimal, and emergency response procedures were often non-existent. In confined plants, gas accumulation led to mass casualties before alarms could be raised. Manual operation increased risk further. Workers frequently adjusted valves, added reactants, or cleared blockages by hand while vessels remained active. A miscalculation in feed rate or sequence could trigger violent reactions. Many fatal accidents occurred during routine sampling or inspection, when pressure was mistakenly believed to be stable. Structural weaknesses were common. Early reactors were built from materials not suited to long-term chemical exposure. Corrosion weakened walls from the inside, often invisible until failure occurred. Repeated heating and cooling cycles caused metal fatigue, increasing the likelihood of rupture without warning. Fires and secondary explosions compounded disasters. Flammable releases ignited nearby equipment, spreading destruction across entire plants. In several recorded incidents, one reactor failure triggered chain reactions that leveled multiple buildings. These dangers were accepted as part of progress. Production demands outweighed safety concerns, and fatalities were often dismissed as unavoidable industrial losses. Only after decades of accidents did standardized safety design emerge, including pressure relief systems, redundant controls, and remote operation. Early chemical reactor vessels demonstrated the peril of scaling reactions faster than understanding them. By enclosing unstable chemistry inside inadequately protected containers, industry created machines that could not forgive error. They stand as stark reminders that chemical power, when unleashed without safeguards, turns efficiency into catastrophe. Dynamite mixing mill. Shock-sensitive explosives at industrial scale. The dynamite mixing mill was one of the most terrifying machines ever used in industrial production, combining volatile chemistry with mechanical motion in an environment where even microscopic mistakes could trigger instant death. Designed to blend nitroglycerin with absorbent materials, these mills operated at the edge of physical safety, earning a reputation as machines that workers entered knowing they might not leave alive. Dynamite production expanded rapidly in the late 19th and early 20th centuries as mining, construction, and warfare demanded powerful explosives. At the heart of this process was nitroglycerin, a substance so sensitive that shock, friction, or sudden temperature change could cause detonation. Mixing mills were built to tame this instability by blending nitroglycerin with stabilizing materials such as diatomaceous earth, but the process itself remained inherently dangerous. Early dynamite mixing mills typically consisted of rotating drums or troughs fitted with paddles, rollers, or stirrers driven by belts or gears. These components moved continuously, spreading explosive material evenly. The danger was constant. Any mechanical fault, foreign particle, or uneven distribution could generate friction or localized pressure sufficient to cause an explosion. Unlike fires or mechanical failures, detonation left no opportunity for escape. Temperature control was a critical risk factor. Nitroglycerin becomes significantly more sensitive when warm and can crystallize dangerously when cooled unevenly. Early mills lacked precise temperature regulation, relying instead on ambient conditions and operator judgment. Seasonal changes alone could turn a stable process into a lethal one. Many explosions occurred without warning during routine mixing, killing entire crews instantly. Human involvement increased the risk further. Workers manually loaded ingredients, monitored consistency, and cleaned equipment between batches. Tools were often made of wood or soft metals to reduce spark risk, but contamination from grit, rust, or hardened explosive residue was common. A single scrape against a metal surface or hardened deposit could trigger catastrophic detonation, structural vulnerability compounded the danger. Mixing buildings were deliberately constructed lightly so that explosions would vent outward rather than inward, but this design offered little protection to those inside. Survivors were rare. Records describe mills reduced to splinters, with fatalities often counted in seconds rather than minutes. The psychological toll was immense. Workers operated under constant stress, aware that skill and caution did not guarantee survival. Many factories rotated crews frequently, acknowledging that prolonged exposure increased the likelihood of fatal error or fatigue-induced mistakes. Over time, safer explosive formulations, remote handling, and automation reduced reliance on direct human operation. Even so, dynamite mixing mills were widely considered too dangerous for sustained use and were among the first explosive production machines to be isolated or eliminated entirely. The dynamite mixing mill stands as one of the clearest examples of industrial danger taken to its extreme. It scaled a substance that violently resisted control, forcing human labor into direct contact with shock-sensitive explosives. In doing so, it transformed manufacturing efficiency into a gamble where every rotation of the mill carried the possibility of instant annihilation. Mercury Amalgamation Mill. Toxic efficiency at the cost of human life. The Mercury Amalgamation Mill was one of the most insidiously dangerous machines in industrial history. Not because it killed instantly, but because it poisoned slowly, relentlessly, and often invisibly. Used extensively in gold and silver extraction from the 16th century through the early industrial era, amalgamation mills achieved remarkable efficiency by binding precious metals with mercury, while sacrificing the health and lives of the people who operated them. Amalgamation mills were commonly employed in mining regions across Europe, the Americas, and later industrial mining centers. Crushed ore was fed into rotating drums, stamp mills, or grinding wheels where mercury was added. The mercury bonded chemically with gold or silver to form an amalgam, which was later heated to vaporize the mercury and leave behind pure metal. The process was simple, effective, and catastrophically toxic. The primary danger was mercury exposure. Mercury was handled in liquid form, poured directly into open machinery, splashed during operation, and recovered by hand. Vapors released during heating were highly toxic, yet early mills lacked ventilation or containment. Workers inhaled mercury fumes, absorbing the metal into their nervous systems without immediate symptoms. Unlike explosive or crushing hazards, mercury poisoning progressed slowly. Early signs included tremors, memory loss, mood changes, and impaired coordination. As exposure continued, workers developed severe neurological damage, kidney failure, blindness, and insanity. Entire mining communities exhibited widespread symptoms, often misattributed to mental illness or alcoholism. Mechanical design amplified exposure. Mills were open, wet, and constantly agitated, mercury droplets into surrounding air and water. Clothing, tools, and floors became contaminated. Mercury entered local waterways, poisoning fish and downstream populations. Workers carried contamination home, exposing families unknowingly. Heating the amalgam was especially lethal. Mercury vaporizes at relatively low temperatures, and recovery furnaces released dense, invisible clouds of vapor. Operators stood nearby to monitor yield, breathing concentrated poison with every batch. Collapsed suddenly during this stage, others suffered irreversible damage over years. Protective equipment was non-existent. Gloves, masks, and respiratory protection were unknown or ignored. Even when danger was recognized, economic pressure ensured continued use. Mercury was cheap, effective, and indispensable to production quotas. Replacing the process was seen as too costly. Mortality was rarely recorded accurately. Workers often lived long enough to deteriorate slowly, losing employment as symptoms worsened. Their deaths were rarely linked officially to mercury exposure, allowing the system to persist for centuries. Eventually, cyanide leaching and other methods replaced mercury amalgamation, driven as much by productivity as by growing awareness of toxicity. Environmental cleanup continues today in regions contaminated generations earlier. The mercury amalgamation mill stands as one of the most devastating examples of industrial danger without drama. It did not explode or crush. It poisoned patiently by trading human health for extraction efficiency. It turned progress into prolonged suffering, leaving a legacy of damage far beyond the walls of the mill itself.